Hi, we are from Group 6 and the title of our project is Demethylation of Toluene to Benzene. Our group consists of 5 members and each of us is assigned with a specific task.
My name is Kucmar Sundarass. My ID is 17003479 and I'll be talking about the introduction and conclusion part.
Hello, my name is Rahul Nair, ID 17004619, and I will be presenting the catalyst screening part.
Hello, my name is Asrajjit, daughter of Kuljit Singh with the ID of 17001700. I'm from Chemical Engineering second year third semester. For this video, I'll be presenting about the determination of bases for reactor design.
My name is Harveindran, ID 17004384, and I'll be explaining the reaction mechanism part.
My name is Ovinderjit Singh. My ID number is 16004784, and I'll be talking about the reactor selection as well as the reactor design.
Our group has been assigned to come up with a catalytic reactor for the reaction demethylation of toluene to benzene. So, demethylation is the chemical process which causes a methyl group to be removed from a molecule. A common way of demethylation is to replace a methyl group with a hydrogen atom, which results in a net loss of 1 carbon and 2 atoms of hydrogen. Toluene and benzene are 2 chemical compounds associated with these. Toluene is a benzene derivative. The key difference between toluene and benzene is the inclusion of toluene in a methyl group, because benzene does not have methyl group attached.
For the catalyst screening, it is very important to consider several factors before selecting the desired catalyst. These factors may include selectivity, conversion, activity, and stability. The selected catalyst is the alumina-supported nickel catalyst, but the selectivity of these nickel-based catalysts are very poor. Thus, it is important to modify the catalyst to achieve a better performance. Table 1 shows a comparison between the different types of nickel-based catalysts. It is obvious that modification of nickel by chromium with acid, also known as HPA and LiHPA, has the better toluene conversion and activity, but LiHPA will be chosen due to its higher selectivity. Another commonly used catalyst is the RH-based catalyst, also known as rhodium-based catalyst. Table 2 below shows a comparison between the RH-based catalyst and the newly developed catalyst. It can be observed that the toluene conversion and benzene selectivity of all 3 catalysts are very similar. However, the acid modification on the nickel has a better sulfur tolerance. Thus, it can be concluded that the nickel-based catalyst with the modification of chromium and acid will be the primary source of catalyst in our reaction.
This is the main reaction. 1 mole of toluene reacts with 1 mole of hydrogen to produce 1 mole of benzene and 1 mole of methane. The byproducts produced by the dimethylation of toluene are diphenyl, naphthalene, and other heavy carbons. The example below is for production of diphenyl. 2 moles of benzene will produce 1 mole of diphenyl and 1 mole of hydrogen. And according to Grotov, as toluene conversion is more than 60%, benzene is also decomposed by consecutive reaction. As you see the example below, benzene will decompose into more methane.
The importance of bases. What is basis? Basis is a very important word in chemical engineering. Physical operations such as temperature, pressure, molar flow rate, and mass transfer plays a very large part. For instance, in our process, which is a demethylation of toluene to benzene, basis is important in designing the reactor. Moreover, the aim is to reach logical conclusions concerning the following principal features of the reactor. Firstly, the overall size of the reactor is general configuration and the more important dimension of any internal structures. Secondly, the exact composition and physical condition of the products emerging from the reactor. The composition of the products must of course lie within any limits of the inlet composition of the process. Thirdly is the temperature, and lastly is the operating pressure within the reactor and any pressure drop associated with the flow of the reaction mixture. In this slide, as we know, the main reaction, which is toluene plus hydrogen, will produce benzene and methane. Below is the table included, which includes all the parameters such as temperature, pressure, mass flow, molar flow, and not forgetting mole fractions. The input and output composition is inserted as well for toluene, hydrogen, benzene, and fuel gas.
Moving on to the reactor specifications, our reactors has been set based on this table below. Now the type of reactor that has been chosen is the packed bed reactor because it is a single bed reactor, it has high conversion per unit mass of catalyst, it can achieve high benzene selectivity and satisfactory toluene conversion, and it has low capital cost. As for the optimum operating conditions, based on our journal articles, it has been set to be at 40 bar as well as 873 Kelvin. As for the type of catalyst, we have chosen the alumina based NiCra LiHBA catalyst, and for the reactor volume, based on our calculations, it has been set at 17.2 meter cube. As for the initial flow rates, toluene comes in at 108.3 kmol per hour as well as the hydrogen stream that comes in at 301.7 kmol per hour. And since the amount of catalyst involved in the process is high, the common plug flow reactor or PFR as well as the continuous third tank reactors STR are not recommended because both reactors are more suitable for reactions without catalyst involved. In our reactor design, we will focus on the design of packed bed reactor, which assumes that it has a steady state operation, perfect mixing, isothermal, and no pressure drop. Reactor configuration and loading is shown based on this diagram on screen. Moving on to the calculation sections, by applying the ideal gas law, we could obtain the initial concentration of the toluene stream. Next, since this is a packed bed reactor, by substituting the values into the packed bed reactor formula, we would determine the weight of catalyst to be 12,194.59 kilograms. And based on that, we could conclude the volume of reactor to be 17.2 meter cube. As for the regeneration of catalyst, alumina-based bimetallic catalyst NiCra LiHBA will undergo catalyst deactivation after a certain time. Improving the performance is related to an increase in metal dispersion in some cases, an improvement in the interaction between metals that can reduce the effect of temperature compared to deactivation by coking. Therefore, the regeneration process has to be carried out to remove the coke in the catalyst. The loss in bimetallic catalyst activity can be restored by the regeneration done through thermally applying high temperature to remove the coke formed inside the catalyst pores.
In conclusion, our group was assigned to come up with a catalytic reactor for the reaction demethylation of toluene and benzene. After going through few journals and research papers, our group has came up with a suitable catalytic reactor. So the catalyst that we chose to use in our reactor is NiCra LiHBA. Okay, this is because it possesses the activity much better than the other commercial catalysts, such as selectivity and activity. Okay. Next, the reaction can take place in purely thermal THDA mechanism or in the presence of any suitable catalyst. And for the reactor design, we chose the packed bed reactor because it has high conversion rate and can achieve high benzene selectivity. And based on our literature readings, we took the flow rate of toluene to be 108.3 kmol per hour and the hydrogen flow rate to be 301.7 kmol per hour. And based on our calculation, reactor volume was calculated to be 17.2 meter cube. Thank you very much. This is the end of our presentation.